In this chapter, we're going to talk about geometry. And that's a study of objects in space is probably a good way to think about it and how they interact with each other. And geometry, when it was originally developed by a mathematician named Euclid back in ancient Greece, thought, well, what are the underlying rules of geometry so that these rules match up with what happens in real life that we see? So that's how we're going to approach geometry, is in this kind of, it's called an axiomatic way, if you will. And you can think of it as we're going to build up the game geometry. And what does every game have? Well, it has pieces to play the game with and a rule, so you know what these pieces can do. So our bare bones pieces, so just the things that exist, we can't describe them in terms of other things we know because we have to start from somewhere. There are building blocks, and they are a point, a line, and a plane. So a point is just in 0 dimensions. It doesn't have a length or anything like that. A line exists in 1 dimension. You can just go along the line, and lines go infinitely far in both directions. So when I say a line, that's what I mean. A plane is the 2-dimensional analog of a line. So you can think of it, if you hold up a piece of paper in the air and imagine that that goes off infinitely far in each direction that the paper edges are in, then that's a plane. So plane is a 2-dimensional analog of a line. And we'll stop there. You can talk about higher dimensions, but for our purposes, that'll be enough. And when we think of these lines, they're made up of points. So there's a bunch of points that make up a line, in fact, infinitely many. And planes contain lines. So you can put a line in a plane. And of course, since lines contain points, planes also contain points. And I will say for this first video, and this is kind of the same thing that happens for any intro to a topic, you're just going to have to deal with a lot of definitions and jargon for the first video. So this video is going to be lots of definitions and terms, so there's not going to be a lot of doing mathematics in this. It's just mostly getting the language down. All right, a few definitions. So say I have a set of points. If these points are collinear, what I mean by that is they all lie in some straight line. So let me show you by example here. So in this example, here's points A, B, and C. These ones are collinear because I can draw one straight line that contains all of these points. So A, B, and C are collinear, and we usually write that by saying A, B, C. So that's our notation to mean collinear. And it gives us kind of the order on the line that these points are. So this is also saying, here that A, B, and C are collinear. And B is between A and C. So that's pretty nice. We have this nice notation to represent collinear points. A non-example is this set of points. They exist on a 2-dimensional space of the screen that you're looking on right now. But as much as I try to draw a line through all 3 of these points, I can't. Because if I draw it through any 2 of the points, let's try that one, well, there's no way that that's going to pass through C. If I try B and C, there's no way that that's going to pass through A. And A and C, there's no way that's going to pass through B. So these are not collinear points. There's an analog for a plane as well. We call a set of points coplanar if they lie on the same plane. This is a little harder to draw, so you'll have to use your imagination here a little bit. But these points, A, B, C, and D, the way I drew them here, so here's a plane. I want you to imagine all these guys on top of that plane. Like if you drew the dots on a piece of paper and then held that piece of paper up in space. That's how I want you to envision this. And those 4 points are coplanar, we call them. There's no nice notation for that. We just say they're coplanar. A non-example, points that aren't coplanar. Well, let me give you one example anyway. Here's 3 points. And we'll say later that 3 points can always be on the same plane. But imagine this 4th point D, and imagine that is beneath the plane here. So that's what I'm trying to denote. So D is underneath this plane. So if you draw a line straight up from D, you get to the plane somewhere here, but I don't want this point, I want D. That's how I want you to envision this diagram here. So they're not coplanar because they all don't lie on the same plane. A few more definitions. So I say a set of lines is concurrent if they're coplanar, so they all lie on the same plane, and they intersect at the same point. So this example here, these 4 lines are concurrent since they all intersect at that red point. That red point is part of all 4 of these lines. A non-example, well, there's 2 non-examples here. So one is this one here. So these all lie in the same plane. These are coplanar, the plane being whatever screen that you're watching this on. So here's our 3 lines that are coplanar. But they're not concurrent since they don't all intersect at the same point. You can see that every set of 2 lines here has a different intersection point than if you picked 2 different lines. So these are not concurrent. Another example of lines that aren't concurrent, they'll intersect at the same point, but they're not coplanar. So if you're in a room right now, look at the corner of the room where the front wall and the side wall and the roof meet. And imagine that the lines that are formed around that corner, imagine they go infinitely far in each direction. And you can see at that corner, those lines intersect. So even though those 3 lines intersect at the same point, they're not concurrent because they're not coplanar. They exist in different planes. So there are 2 non-examples of concurrent points. We have a notion of parallel lines as well. Well, what does it mean for 2 lines, 2 or more lines, to be parallel? Well, it means first that they're coplanar. They exist in the same plane. And that no 2 intersect. So here's an example. Here are 3 lines, L1, L2, and L3. And you can imagine these are going in the same direction. They're just moved a little bit in space. These will never intersect if they extend infinitely far. So we call those parallel, since no 2 of them will ever intersect. And the symbol that we use to write down that lines are parallel is this kind of double vertical line here that looks like parallel line. So here, L1 is parallel to L2, which is parallel to L3. So that's what this symbol here means, that double line, that means is parallel to. 2 non-examples, well, here's 3 lines here. But, hey, look, there's an intersection point. Here's that intersection point. So even though, let's label these lines, I'm going to call them L1, L2, and L3. So L1 and L2, these are parallel, but L3 is not, since there is an intersection point with L2, and there will be with L1 as well if we extend both lines. So this set of lines, L1, L2, and L3, is not a parallel set, but L1 and L2, in this case, are parallel. The second non-example is, well, your lines can just exist in different planes. If they exist in different planes, then we're not talking about a notion of parallel either. So in this case, look ahead at your wall in front of you and at a wall to the left of you. And imagine on the wall on the left, there is some line drawn. And in the wall in front of you, there's another line drawn. So those lines do not exist in the same plane. The line on your left wall exists in the plane that's the left wall, if that extended infinitely far in every direction. And the line on the wall in front of you exists on that plane, two different planes. So they're not coplanar, so we don't have a notion of parallel, even if they will never intersect. But lines that exist on different planes, we call this set of lines, they're skew lines. They exist in different planes. All right. So another concept that's going to be important to us is the idea of a transversal of two lines. And those two lines need to be coplanar lines. But I will say, for our purposes, we'll really only care about when those lines are parallel. There's some nice results when we have a transversal of parallel lines. So that's what we're going to care about. So an example of that, we have L1 and L2. They're parallel lines. We know that L1 and L2 are parallel. And since T intersects both of these lines at those 2 points, we say that T is a transversal of L1 and L2. So that's what I mean by a transversal. All right. So in a lot of instances, we'll want to talk about the distance between 2 points. So let's say we have points A and B here. Well, what is the distance? Well, that's just the length of this line segment between A and B. And the way we write that, the notation we use, is we just use AB. So that means the distance. Just list the points, or you could list them in the other order too. BA is fine, whatever makes sense. So if we measure this with a ruler, and that was 4 units, then we'd write something along the lines of AB equals 4. And one more piece of notation. We'll talk about collinear points again here. If we know that A, B, and C are collinear with B is in the middle, then we know that the distance from A to B plus the distance from B to C has to be the same as the distance from A to C. So we know if this is A, and this is B, say, and this is C, well, if this is the distance from A to B, and this is the distance from B to C, we know that, well, if we add those together, we just get the distance from A to C. And let's just do a little quick example to make sure we understand this. All right, so let's suppose that, let's do 4 points, that A is between B and C, C is between B and D, and they're all collinear. And suppose we know that the distance from A to B is, let's say, let's do 3 units. Let's say the units are meters. let's say the distance from A to C was 7 meters. And let's say we also knew the distance from B to D. Let's say that was 9 meters. What I want to find are the other distances. So I want to find the distance from A to D. I want to find the distance from B to C. And I want to find the distance from C to D. So let's do this example here. I'm going to scroll down a bit, give myself just a little more room. Okay, so sometimes it really helps to draw a diagram to keep all this straight. So here's my diagram. Here's A, B, C, and D. And this is just a sketch, so none of these distances I drew are the actual distances or represent the actual distances. It really is just a sketch. And I know that the distance from A to B is 3. I know the distance from A to C is 7. And I'm given that the distance from B to D is 9. Okay, so let's go about finding the other distances. Well, let's do the first one. So this one's quite easy. Looking at my diagram, I know the whole thing. You go from A to B and then from B to D, and that gives me from A to D. So I know that, oh, let me use black here. Since I know that the distance from A to B plus the distance from B to D gives me the distance from A to D, so as long as these middle points match up, you can just say it's the distance from your first endpoint to your second endpoint. Well, we know the distance from A to B and the distance from B to D, so we can just fill that in. We get that 3 plus 9 equals the distance from A to D. So that tells us that 12 meters is the distance from A to D. So I know this guy is 12 meters. Okay. Similarly, let's see if we can do the other ones now. Okay. Let's find BC next. So the distance from B to C, well, we know the distance from A to B, and we know the distance from A to C. So we can use our distance equation again. AB plus BC equals AC. We know AB is 3. We're looking for BC, and we know AC is 7. So solving this, I think it's pretty easy to see, just subtract 3 from both sides, that the distance from B to C must be 4 meters. So we can put that in here. This is 4, and one can put the whole thing in here. This was 12. And finally, well, we need the distance from C to D. And there's loads of different ways of doing it. I'll do it this following way. Again, no way is better than another. But I know the distance from B to C and from B to D, so I can solve for the distance from C to D. So let me go ahead and do that. So I know that, oh, I don't want A, I want B. The distance from B to C plus the distance from C to D equals the distance from B to D. And I know the distance from B to C is 7. No, sorry, is 4. Let me put that in here. 4 meters. So that is this distance here from B to C. I'm looking for the distance from C to D, and I'm given that the distance from B to D is 9. And again, very simply, subtracting 4 from both sides, we get that the distance from C to D is 5 meters. So we found all of our distances here. That's great. Maybe I'll put that in yellow as well. This distance, we said, was 5 meters. Great. Okay, so we've solved this problem using distances. Hopefully that gives you some good practice. Not so much on problem solving. This one was quite easy. But definitely on using this notation for distance, it will come up quite a bit. Okay. For lines and line-like objects, like line segments, which are, you can think of as pieces of lines, so they're not infinite. They're finite in both directions, and they have endpoints. And rays, which are halfway in between. They're infinite only in one direction and have one endpoint. So we're going to talk about how to name these. And the first thing I can say is you can just kind of give these their own names as well. So if I want to name this guy just L for line, and this guy maybe A, line segment A, and this guy can be ray R, I could do that if I wanted to. But you can name them in terms of points on them. So for lines, you can just pick any old 2 points on your line, say A and B, and the name of it is line AB. So you write down AB, and you put a line over it. Note there's nothing particularly important about the direction either, so if you wanted to, you could name it line BA. So that's not particularly important either. With a line segments are named by their endpoints. So that's important. These guys are endpoints. And again, with a line segment, there's no particular direction with them. So if you wanted to name it BA instead, you can go right ahead. Now, a ray is a little bit different because it only has one endpoint. So when you name a ray, you always have to include the endpoint and some other point on your line. So in this case, it'll be B. So this ray will have the name AB, where you put a ray over top, where the endpoint is over the endpoint point. So this is good. Or you could do it the other way for whatever reason. Maybe it makes sense in a different situation. You wanted to write that. That's good as well, since your endpoint point is over the endpoint of your ray there. But not, these are no good. If you had AB going this way, or BA going that way, since your ray, in this case, the endpoint of the ray that you drew and the endpoint point aren't over each other. So these are not good. Now's a good time to start talking about the rules of the game geometry. All of the previous stuff we talked about, we're developing the pieces and names. So, how do the rules of geometry work? Well, Euclid discovered that some good rules for the game geometry, so that the way geometry works in the mathematical world matches up with how geometry works in the real world, are as follows. And keep in mind, these are rules in the way that we can't really prove them or show that they work from simpler things. These are just things that we're given. So the math word for that is either postulates, or another word you might see is axioms. So they're just rules that we take for granted. They're the base rules of this game, geometry. And we can build up new, more complicated rules out of these rules that we're given. We're going to include 2 more postulates later on when we get talking about angles. But given those, we can build up new rules to our game as well. But the 5 postulates, or 5 rules of the game geometry, says that if you have 2 points, it doesn't matter which 2 points, you can always find a line that contains them. And in fact, there is only one line that contains them. So there is exactly one line going through any 2 points. All right. The second postulate has to do with planes. And it's kind of the same idea. This one might be a little bit harder to think about. But you can try it if you have a couple of friends. Get your friends to hold their finger in a random spot in space, close enough together, and you'll always find a way for a piece of paper to touch all of their fingers. If you had something stiff, it might be a little bit better. So maybe a thicker piece of paper or a piece of cardboard so that it doesn't bend. But you'll always be able to find a way to get that piece of paper or piece of cardboard to touch all of your 3 friends' fingers, which is very interesting. But the rule is basically, it's kind of the same thing, saying if you have 3 points that aren't in a straight line, there's exactly one plane that contains them, where those points are on that plane. The third rule of the game geometry is if you do have a plane, here's our plane here, and you have 2 points on that plane, then the line that contains those points also lies on that plane. And that kind of makes sense, right? So if your plane is a piece of paper that you're drawing on, if you draw 2 points on it and you connect them via a line, that line is on your paper. So no matter what, that line remains on the plane where those 2 points are. The fourth postulate says that if you have 2 planes and they intersect, then the intersection of them is a line. So this is kind of harder to draw, but let me try. So here's our first plane. And let's say we have a second plane going through it. I'll do it in green here. So let's say it intersects here, and I'll draw kind of the back of it as well. And they go off infinitely far as well. So imagine the blue one is kind of straight up and down, like you're holding a piece of paper directly in front of you. And the green one is kind of flat going through it. I know the drawing isn't the best, but that's what I'm trying to get across here. Again, if you look around and you find right now the wall in front of you and say the ceiling, where they meet, you can imagine them as pieces of a plane, and you can imagine where they meet is actually a line. So that if everything extended infinitely far, then the line of the intersection of the wall in front of you and, say, the ceiling in front of you would be a line that extends infinitely far in both directions. So that's what I mean there. And the final postulate is basically saying that, if you have a line, you can always think of it as a number line. So you can talk about, basically it lets you talk about distances. And what's nice is it also says there's infinitely many points on your line because there's infinitely many numbers on a number line. And I have this infinitely many points kind of with an asterisk there. And we're not going to get into it too much in this course, but there's different types of infinity, believe it or not. So there's basically 2 types of infinity that we care about in some sense at this level. But countably or listably infinite, those things are like the whole numbers or the integers. You can list them. You can write them down in some sort of order where you can say this is the first element, this is the second element, this is the third element. Even if they go infinitely far, if you're clever about them, you can list them. But there's a larger infinity, which is a non-listable infinity or non-countable infinity. And the real number, so that's all your numbers, including fractions and pi and square roots and all of these irrational numbers as well, that's non-listable or uncountable. Again, we won't get into it too much in this course, but just for your knowledge, and if you're interested more, you want to look up uncountably infinite, and you'll kind of see the difference between uncountable and countably infinite. So there are 5 postulates. We're not going to worry too much about these in this course, but just know that everything that we do in this course relies on these base rules of the game. We can always find a line between 2 points. We can always find a plane between 3 points. We can always find a line on the same plane that joins up 2 points. The intersection of 2 planes is a line, and there's infinitely many points that are ordered like the number line on every line.